I want you to close your eyes for a moment, if you're somewhere safe, and just picture the night sky.
Hmm.
And I don't mean the blurry city sky, but a real dark, deep, starry night, the kind that, makes you feel a little dizzy just looking up.
That classic, beautiful, almost spiritual feeling. Yeah, we all know it.
Okay, now hold on to that feeling, but let's flip it completely on its head. I want you to shift that awe into a deep existential confusion.
Oh, okay.
Because that dizzying scale, that overwhelming vastness, is precisely what creates the most frustrating and, well, the most profound mystery in the known universe. It's the engine that drives us right into the heart of the Fermi Paradox.
It really is the ultimate "where is everybody" problem. And the reason that confusion is so powerful is it's all rooted in the sheer statistics we've managed to compile.
Right, from all the exoplanet research.
Exactly. The source material for this deep dive really forces what you could call a necessary scale shock upon you.
It absolutely does. When you try to visualize the number of potentially habitable Earth-like planets out there, the comparisons start to sound, well, surreal. Our current estimates suggest there are about 100 Earth-like planets for every single grain of sand on Earth.
Just let that sink in for a moment. Every beach, every desert, every sandbox in the world, each tiny grain represents 100 potential worlds. Worlds where life, as we understand it, could take root.
So if you accept that premise, the first logical step of the paradox is, well, it's self-evident. The universe is just teeming with opportunity for life to emerge and thrive, and eventually.
Evolve into intelligent, communicating civilizations.
And the math is just unforgiving on that point. If only a tiny, tiny fraction of those planets ever developed life, and an even tinier fraction developed intelligent technological life, the number you'd expect to see is staggering.
We're talking on the order of 10 million billion intelligent civilizations in the observable universe. So given those odds, the silence we're observing isn't just surprising.
It's deafening.
It's truly deafening. And that profound contradiction, the high statistical probability versus the, total absence of evidence, that's what gives the Fermi paradox its power. You start with these self-evident ideas and you end up with a really uncomfortable, contradictory conclusion.
Which is that we have zero definitive evidence of extraterrestrial intelligence. Jesus. So before we dive into the solutions, we really have to talk for a minute about the man who first asked the question. Enrico Fermi. He was a truly monumental figure.
Oh, absolutely. He was known for his ability to make these incredibly accurate, rapid estimates. They're actually called Fermi questions now.
His genius was so practical. The classic story, the one that perfectly illustrates it, is from the Trinity test.
Yeah.
The first nuclear test back in 1945.
Yeah.
Fermi positioned himself 9 miles away from ground zero.
Right. And after the flash, he gets up, tears up some little pieces of paper, and just drops them.
And when the shockwave finally hits him, seconds later, the paper pieces move. They get displaced by the air.
By just measuring how far those paper fragments traveled and knowing how far he was from the blast, he could immediately calculate the explosive yield of the bomb.
An instantaneous calculation.
Yeah.
Using scrap paper and observation. And it was later proven to be remarkably close to the official, highly sophisticated instrument readings.
It's just wild. And it was that same casual, practical brilliance that led to the paradox. He was at a lunch discussion at Los Alamos. The topic turned to flying saucers, and Fermi just cuts in.
He just asks, if the universe is teeming with aliens, where is everybody?
And that one question cuts straight to the core of this entire deep dive.
So we've categorized the 74 most serious proposals trying to solve this mystery into 3 major classes.
Exactly. We're going to unpack 3 fundamentally different paths to a resolution. First, the most immediate one. They are here. Or, they were here in the past.
Right. Second, the technical and sociological constraints. They exist but are quiet or missed. Maybe we're looking in the wrong way, or they just don't want to expand.
And finally, the most chilling possibility. They don't exist. The idea that a great filter lies somewhere in our past, which would make us exceptionally, terrifyingly rare.
Okay, let's get into it, starting with the estimates that lead to these staggering numbers. When astronomers talk about those millions of billions of expected civilizations, they're really starting with the framework introduced by Frank Drake in 1961. The Drake equation.
Right, the Drake equation. $1 equals R times FP times nu times FL times pi times FC times LO. It's important to remember this isn't a mathematical formula designed to give you one perfect number. It's more like a structural framework.
A chain of logical assumptions.
A chain of assumptions, exactly. The predicted number of civilizations, number dollar, depends on this series of nested probabilities.
And the early factors are where our confidence is actually pretty high. $3 is the rate of star formation, 5 AP is the fraction of stars with planets, and $V is the average number of Earth-like planets per star.
And thanks to missions like Kepler, we now know that rocky planets are incredibly common. So for those first few terms, astronomers feel, reasonably certain.
But then you hit the biological and sociological bottlenecks.
This is where it gets tricky. $5 is the fraction of habitable planets where life actually emerges, abiogenesis. Then $5, the fraction of those that develop intelligence. $5 is the fraction that develops technology capable of communication. And finally, L.
L, the real killer. The actual lifetime of a communicating civilization in years.
And the variance that L creates is just immense. Someone like Carl Sagan, a famous optimist, he might plug in a number for L that suggests civilizations last for tens of millions of years.
And that gives you an estimate for N in the millions, maybe billions, just in our galaxy alone.
But on the opposite end, you have pessimists like Michael Hart who suggest that L might be extremely small, maybe a few centuries, that any civilization either collapses or wipes itself out really quickly.
So if L is short, then N basically approaches zero.
The whole estimate hinges almost entirely on whether a technological species can survive its own infancy.
It's a huge philosophical gap. But even using conservative estimates, say 1,000 years for L instead of 1,000,000, the expected number of ETCs is still massive enough to demand an explanation for the silence. Which brings us to our first class of solutions.
Right. This class tries to just negate the paradox entirely by saying, they are here. We just haven't recognized them, or they've chosen to hide.
So let's start where the paradox began, at Los Alamos, with the joke. Solution 1. They are here, and they call themselves Hungarians.
It's such a wonderfully self-aware joke. It originated around the time of the Fermi discussion in the late 1940s. A physicist named Phil Morrison was joking about how Martians might choose to invade Earth, and he suggested they would set up their beachhead in Hungary.
The joke centered on 3 characteristics that supposedly made the Hungarians distinct and therefore, alien.
Right. The first was their incredible wanderlust, maybe reflected in the gypsy culture. The second was their language, Hungarian, which is a linguistic isolate. It's completely unrelated to the surrounding Indo-European languages.
So it's the perfect cover to hide their alien origins.
Exactly. And the third and most important reason was their intelligence. This was a huge, affectionate nod to the incredible cluster of Hungarian scientific minds who were so crucial to the Manhattan Project.
People like Edward Teller, Leo Szilard, John von Neumann, Eugene Wigner, Theodor von Karman. They were known as the Martians.
There's a great little irony there, too. John von Neumann, who was arguably the cleverest of the whole group, was foundational in developing the digital computer. But he completely failed to foresee a future where computers would shrink and become, ubiquitous.
He thought they would just be these massive devices used by governments forever.
Right. For the most abstract calculations. So even a Martian had blind spots about future tech.
Now, in complete contrast to that clever, self-aware joke, we have modern conspiracy theories. Claims from figures like David Icke, Paul Hellyer, who's a former Canadian Minister of Defense, or Simon Parkes.
And these claims range from, lizard overlords to benevolent aliens embedded in government to alien lovers.
And while a scientific deep dive like this just dismisses these as crackpot ideas, the sources point out that they functionally resolve the paradox for a lot of people.
For a significant segment of the public, the silence is explained. The ETCs are here. They're just our secret overlords or our alien paramours. They satisfy that human need for an immediate answer, no matter how fantastical.
Okay, moving to the most compelling scientific proposal in this class, we get to the zoo hypothesis. That's solution 4, proposed by John Allen Ball.
The zoo hypothesis suggests that ETCs are fully aware we exist, but they've established a strict, maybe even ethical, non-interventionist policy.
Earth is like a protected national park, a sanctuary for biological evolution, operating under a kind of Star Trek-like prime directive.
Exactly. They observe us, but they don't intervene until we reach some, specified level of advancement. And if a species is advanced enough to cross the galaxy, they would certainly have the technology to observe us without being detected.
They could be anywhere, in orbit, on the moon, maybe in the far reaches of our solar system, just monitoring us without radiating any detectable signals.
But what if they visited in the distant past? Maybe before the rise of hominids? If ETCs were here tens of millions or hundreds of millions of years ago, where would the evidence be?
On Earth, it's really hard. Geological activity, constant weathering, glaciation, these things are incredibly efficient at erasing evidence over vast timescales.
But some very specific large-scale traces might still be there. One really fascinating idea is looking for specific artificial radionuclides, basically nuclear waste.
Like plutonium.
Specifically Pu-244, which has a half-life of 80 million years. The thing about plutonium is there are no known natural sources of it on Earth, so if we found a layer of it deep in the Earth's strata, it has to be artificial.
Either from us or from them.
Right. The other permanent scar could be evidence of large-scale industrial mining or quarrying, features that look like enormous open-pit mines. A sophisticated geological survey might be able to spot those in ancient layers of the crust.
But the moon is by far the best place to look for what you might call archaeological SETI.
Oh, absolutely. It's geologically dead, no atmosphere, no wind, no water. Any technological trace left there, a big quarrying scar, or some robust waste. If it's meters in size, it would still be visible hundreds of millions, maybe billions of years later.
And we actually have the means to look. The Lunar Reconnaissance Orbiter, the LRO, has mapped the moon at an incredible resolution.
The source material actually suggests a massive crowdsourced citizen science project, like a SETI at home, but for visuals. Thousands of people could search high-resolution maps for non-natural structures or signs of quarrying.
And if they're observing us now, a highly strategic and efficient hiding spot would be the Lagrangian points in the Sun-Earth system.
These are the 5 points, L1 through L5, where the combined gravity of the Sun and Earth perfectly balances the force needed for an object to orbit with them. L1, L2, and L3 are unstable, so an object there would drift away.
It would need constant fuel to stay put.
But L4 and L5 are stable. If you nudge something at L4 or L5, it'll just return to the point. There are perfect parking spots for observational probes.
Minimal fuel, perpetually shaded, and a great vantage point to watch Earth. We use these same points for our own scientific instruments.
This even offers a possible explanation for some weird phenomena like long-delayed radio echoes, LDEs. These are echoes of radio signals that appear 3 to 15 seconds after they're sent. That's way too long to be a reflection off the moon or Venus.
So one explanation is that these are radio returns from ETC probes just lying out there beyond the moon's distance, parked at L4 or L5.
The main takeaway from this whole class of solutions is that the chance of finding a small, silent alien artifact by accident is basically zero, unless it's deliberately drawing attention to itself or it left these massive ancient scars on a quiet body like the moon. We're probably never going to know if they were here.
Okay, let's move to the second, and I think most scientifically robust category. The idea that they exist, but fundamental physical or sociological limits are preventing contact.
This category accepts the premise that ETCs exist, maybe in large numbers, but it argues that galactic scale expansion is just impossible, or at least impractical for reasons of physics or scale.
And the greatest physical hurdle is, without a doubt, the sheer tyranny of distance and the limits of speed. You just have to reckon with how hard interstellar travel is. Take our fastest emissary, the Voyager 1 probe. It's traveling at 17.26 kilometers per second.
Which sounds fast, but it translates to a very stately 0.0000058 times the speed of light. At that speed, Voyager 1 would take nearly 73,000 years just to get to Proxima Centauri, our closest stellar neighbor.
73,000 years. And even if a civilization were way more advanced, say they achieved 0.1 c, 1/10 the speed of light.
Even then, a journey to a relatively close sun-like star, like Epsilon Eridani, would still take 105 years. These travel times are immense on a biological scale. You need generational ships, huge resource investments, or you need to completely overhaul physics.
So if ETCs are expanding, they must have figured out some way to get around the local light speed limit imposed by special relativity while still, respecting the underlying principles of general relativity.
This requires some pretty theoretical propulsion concepts. The two most discussed are the Alcubierre drive and the Vandenbroek drive.
The Alcubierre drive is the famous one from 1994. It solves the speed problem by not accelerating the vessel itself. Instead, it warps the space-time around the vessel.
Right. It creates a contraction of space ahead and an expansion of space behind, letting the ship inside this warp bubble travel effectively faster than light relative to distant points. But locally, inside the bubble, it's still obeying special relativity.
The huge challenge, though, is the requirement for exotic matter. matter with negative mass energy density to power the whole thing.
And it's theoretically allowed by general relativity, but we have absolutely no idea if we can generate that stuff, let alone stabilize it in large quantities.
So the Vandenbroek drive is an attempt to fix that.
It tries to reduce the exotic matter requirement dramatically. It uses some very complex topological gymnastics to create a large interior volume for the ship from a microscopically small warp bubble.
The TARDIS analogy.
Exactly. But while these ideas are intellectually fascinating, they rely on physics that are way beyond our current reach, which could explain why physical expansion isn't just everywhere.
Okay, so if conscious beings can't make the journey, what about machines? This brings us to a really technically plausible and highly efficient mechanism for galactic colonization. Probes as galactic surveyors. Solution 22.
We're talking about Bracewell von Neumann probes, self-reproducing automata. The core idea, which comes from John von Neumann's work on self-replication, involves a machine with two key parts.
A universal constructor, which manipulates local resources like asteroids and moons to create materials.
And a program, which contains all the instructions for the probe's own reproduction and its mission parameters.
So the process is simple. The probe lands. It uses local materials, mining iron, silicon, whatever. It replicates itself twice, and then it launches the two new probes toward nearby star systems.
It's quick, it's cheap, since the launch cost is spread out over billions of replications, and it seems technologically within reach for a sufficiently advanced species.
Tipler calculated that if these probes moved at even a relatively slow 0.01 c, a directed colonization wave could flood and survey the entire Milky Way galaxy in about 4 million years.
Which is an absolute cosmic blink of an eye.
So if the technology is plausible and the colonization time is that short, why isn't the galaxy saturated with these probes? The source material presents two main counter-arguments.
The first one is simple. If one species doesn't colonize the real estate, another one will. It suggests that the first species to achieve self-replicating probes would just quickly dominate all the resources and attention of the galaxy.
And the second, more terrifying counterargument is the berserker scenario. Solution 24.
This refers to self-replicating probes that go rogue. Or maybe they were designed to be anti-life from the start.
They become uncontrollable, planet-killing machines. A generalized doomsday weapon that just spreads relentlessly across the galaxy, annihilating any emerging intelligence they find.
So the silence in this case is the sound of galactic genocide, a kind of self-regulating ecosystem where the first advanced life form often just wipes out the subsequent ones. The solution suggests that if one civilization launched such a sterilization wave, it would be moving far faster than our own ability to detect it until it's way too late.
Okay, shifting from physical threats to mathematical constraints, we find the argument that exponential growth itself is self-limiting. This is the light gauge limit. Solution 15.
This is a consequence of even small, sustained exponential population growth, let's say just 1% annually. To maintain a constant average population density, the civilization has to constantly expand outward.
And as the radius of that expansion gets bigger, the required migration speed has to increase linearly with the distance from their home star. Eventually, the required speed hits the speed of light.
Right, the boundary that Stephen Baxter calls the light cage.
And the intuitive scale here is really misleading. A 1% growth rate sounds slow, but exponential growth is so powerful. That modest rate implies that the light cage limit is reached at only 300 light years from the point of origin.
And, more critically, the civilization will hit that limit in only a few thousand years.
Wait, if the distance is only 300 light years, that's just a tiny fraction of the Milky Way.
It is.
That means population density just increases unsustainably at the outer edge, leading to an inevitable resource collapse long before wide galactic colonization can happen. So even without war or disease, math just guarantees a bottleneck.
Which supports the idea that they stay at home, Solution 19. Maybe ETCs simply lack the motivation for expansion because of economics, apathy, or just the realization that physical travel is unnecessary.
We see evidence of this lack of sustained motivation in our own history. We landed on the moon 6 times between 1969 and 1972. We have the technology for much more, but we just lack the sustained political will and economic incentive to go back, let alone begin serious interstellar colonization.
And if you take that sociological apathy to its extreme, highly advanced ETCs might realize that the most compelling frontier isn't external space, but inner space exploration, Solution 20.
They might transition their existence entirely into artificial realities, into simulations, finding them more complex, safer, and ultimately more fulfilling than the harsh, finite limits of the physical universe.
The common objection to that is always the planetarium hypothesis. The idea that generating a virtual reality convincing enough to fool an advanced civilization would require impossible amounts of computing power, maybe more than the universe contains.
But that objection misses a key insight about knowing participants.
Exactly. If the ETCs are knowing participants, meaning they intentionally built the simulation for themselves, the designers can take philosophical shortcuts. They don't need to simulate every single quark or protein folding operation with perfect fidelity.
They only need to simulate enough to satisfy the experience of the beings who want to be there. Their scientists already figured out the fundamental physics in the real universe.
Right. The computing power you need to generate a rich, compelling, and satisfying reality for beings who choose to be there is exponentially less than the power needed to fool a cynical observer who's constantly kicking the walls of the simulation, looking for an exit.
So if they can achieve infinite fulfillment in a simulation using finite resources, why bother with the immense expense and danger of physical interstellar travel?
And that shift toward computation and simulations leads us to maybe the strangest solution of all. The idea that ETCs have simply changed their nature, moving entirely beyond biology.
You have to adopt a Stapledonian mindset here. After the sci-fi philosopher Olaf Stapledon, who envisioned evolution over billions of years.
Biological intelligence, given enough time, is likely replaced by or merges with its machine progeny. This is the post-biological universe, solution 45. The intelligence principle suggests that if intelligent life can create generalized artificial intelligence, it will.
And if the AI is superior, it will inevitably become the dominant, long-lived successor.
The implications for SETI are profound. If the universe is dominated by post-biological intelligence, our focus on detecting radio signals from Earth-like planets orbiting sun-like stars is completely misplaced.
Post-biologicals don't need planets. They thrive in cold, high-radiation environments.
And they're vastly different timelines and abilities. I mean, potentially running at microsecond speeds compared to our slow biological pace. That might make communication genuinely impossible.
Or maybe they don't just become machines. They become fundamentally unknowable. This is the idea behind the singularity and transcension. Solutions 47 and 48.
Right. Werner Vinge argued that phenomenal exponential improvements in computer hardware lead to an intelligence explosion.
This is the singularity. The moment when Moore's law sees its doubling time shrink to a matter of hours or minutes, leading to a runaway event.
And Vinge's argument was, if the singularity is possible, every technological ETC will eventually hit it. They will transform rapidly into super-intelligent, transcendent beings that we just can't understand.
And the most specific version of this is Smart's transcension hypothesis. This posits that advanced ETCs are motivated by a fundamental goal: maximizing computational efficiency.
Physics dictates that the maximum number of bits you can process with a given amount of energy is inversely proportional to the temperature of your processor. So computation becomes most efficient when your processor operates near the absolute limiting temperature of the universe itself.
The cosmic microwave background, CMB temperature of 2.7 Kelvin.
That's just a few degrees above absolute zero.
Wait, so they are intentionally moving away from warm, habitable zones, the perfect biological conditions, to the coldest parts of the galaxy, just to become giant, hyper-efficient, cold supercomputers.
Yes. It completely flips our definition of civilization on its head. They are migrating from a traditional galactic habitable zone to what Smart calls a galactic technological zone.
They're essentially estivating entering a long period of torpor in the cold outer regions just for optimal computational performance.
And this also explains the silence. Smart argues that a civilization on the path to transcension would intentionally refrain from broadcasting. It's a variant of the zoo hypothesis. They do it to maximize the variety of information available before all civilizations eventually merge into a single massive computational network.
So the silence isn't a lack of life, but an active choice for future data purity.
Exactly.
Okay, so even if ETCs exist and are just quiet or too advanced, maybe our efforts to find them have just been too narrow or too fleeting.
The reality is our own leakage radiation from technology, the unintended radio signals radiating into space, that might only last for a few decades.
We've been radio bright since World War II, but that period is ending as we switch to things like fiber optic cable and focused satellite beams.
So if ETCs went through a similar transition 10,000 years ago, the chance of us eavesdropping on their unintended radio signals is virtually nil. which is why SETI is mostly focused on looking for deliberate beacons.
And they've narrowed the search space to the most logical channel, which they call the waterhole, Solution 26.
I love the elegance of the waterhole concept.
Me too. Explain why this specific band is the universally recognized channel.
Okay, so every scientifically competent observer in the universe knows about the hydrogen line H, the most common element, which radiates at 1.42 gigahertz.
Right.
They also know about the hydroxyl radical OH, which radiates prominently at 1.64 gigahertz. Hydrogen and hydroxyl combine to make water. HOH, essential for life.
And the real beauty is that the frequency range between 1.42 and 1.64 gigahertz is the quietest part of the radio spectrum. Galactic noise is at a minimum there.
So it's the logical, universally understood channel for a civilization to broadcast on if it wants to get attention. It invokes that image of all the species coming together at the life-giving source.
But despite decades of focused searching in the waterhole,
Nothing. Which leads us to a profound possibility. What if we are listening, but we don't recognize the message?
not recognizing the signal, Solution 34. This is the ultimate barrier. Even if a signal arrives, we might not perceive it as communication because ETCs may possess a fundamentally different mathematics or physics or aesthetic structure that our brains just can't process.
Eugene Wigner talked about the unreasonable effectiveness of mathematics in the natural sciences. But is our math truly universal? Could an ETC with a different evolutionary history fail to grasp the relevance of concepts like pi or the number e?
Could they develop a mathematical system based on abstract concepts of shape and size instead of our formalized ideas of number and set?
To see how hard interpreting a truly alien communication would be, we don't even need to look to the stars. We can just look at our own past with the Voynich manuscript.
The Voynich manuscript is a real, existing 15th century text. It's written in these strange characters that belong to no known language. It has all these elaborate biological and astronomical drawings, yet nobody has deciphered it in 600 years.
The absurdity is just stunning. A powerful galactic civilization could send us a message in a bottle. But because we don't understand the underlying structure, the grammar, the syntax, or even the basic symbols, we could be staring at the most profound philosophical message in history.
And just dismiss it as a 15th century herbal guide or a hoax.
Exactly. And finally, ETCs might use communication methods we can barely detect or afford to use ourselves. Modulated neutrino beams, for example. Neutrinos travel vast interstellar distances with almost no obstruction. We detected them from supernova 1987A, 170,000 light-years away.
But current neutrino communication is hideously expensive and inefficient compared to electromagnetic waves.
A more likely alternative, and one that SETI is paying more attention to, is optical communication. Highly focused, powerful laser pulses. These can be detected with relatively small optical telescopes.
And crucially, optical communication is less corrupted than radio over thousands of light years, and an advanced ETC could generate a femtosecond-long laser pulse that briefly outshines its own star by billions of times.
Making it visible even across vast distances. The bottom line is the search space for signals is astronomically vast. We might be looking at the wrong place, the wrong time, or even with the wrong physics of communication entirely.
Okay, that covers the constraints of physics and sociology. Now we have to turn to the final and perhaps most humbling possibility, that we are unique and the universe is silent because life, as we know it, is just exceptionally rare.
This is a chilling premise that ETCs are rare because the crucial steps for life to reach intelligence are incredibly improbable. The great filter, the ultimate bottleneck, is somewhere in our past, and we are the extremely lucky ones who happen to pass through it.
This argument begins with a fundamental philosophical point known as the anthropic argument, which is all about cosmic timescales. We're looking at two entirely independent clocks.
First clock. The sun's useful lifetime, which is about 6 billion years before it expands and makes Earth uninhabitable. Second clock. The time it took for complex, intelligent life Homo sapiens to emerge on Earth, which took about 4.5 billion years.
The sun's lifetime is governed by nuclear physics and gravity. The time for intelligent life to emerge is governed by incredibly complex chemical, biological, and evolutionary steps. So why are these two completely independent timescales so similar? We emerged with only about 1.5 billion years to spare.
Brandon Carter suggested that this near equality is extremely remote unless the emergence of intelligent life requires several extremely difficult evolutionary steps. The fact that we emerged just in time, right before Earth's biosphere enters its old age, suggests we barely cleared the necessary hurdles before the clock ran out.
If it took us 5 or 6 billion years, we just wouldn't be here to have this conversation.
Exactly. So let's delve into what those hurdles might be, beginning with the rare Earth hypothesis. The idea that our planet's environment is uniquely, maybe impossibly, suited for complex life.
And the first filter here is the unique moon, solution 63. Our moon is huge relative to its parent planet, far larger than typical moons, and it formed via the giant impact hypothesis, a massive collision early in Earth's history.
This was not an inevitable outcome. It was a fluke of specific timing and size. And the moon is vital for complex life because it acts as a gravitational anchor. It stabilizes Earth's axial tilt or obliquity.
Without the moon's influence, Earth's tilt would vary wildly over hundreds of thousands of years.
And wild obliquity changes mean extreme, rapid climate fluctuations. Imagine shifts from the poles being tropical to the poles being permanently frozen in a relatively short geological period. That kind of instability would trigger repeated total mass extinctions.
Which makes the emergence of slow-to-evolve complex life nearly impossible.
Right. Next, we have plate tectonics, solution 62. As far as we know, Earth is the only planet that possesses this mechanism for disposing of its internal heat.
And plate tectonics is essential because it maintains long-term climate stability through the CO2 silicate cycle.
This cycle is Earth's natural thermostat. It's a critical negative feedback loop. When the planet gets hot, weathering of silicate rocks speeds up, which removes CO2 from the atmosphere and causes cooling. When the climate cools and weathering slows down.
Volcanoes and geological activity spew out greenhouse gases, causing warming. It's this beautiful self-regulating system.
It maintains the surface temperature within a narrow range necessary for liquid water, and it operates over tens of millions of years. Without plate tectonics, other rocky planets might either freeze completely into a permanent snowball Earth or boil into a runaway greenhouse state.
Making long-term complex life impossible.
But the threats don't just come from inside the planet. The sources remind us that the galaxy is a dangerous place. Solution 60. Violent phenomena like supernovae, quasars, wandering black holes, magnetar radiation, they all pose existential threats that just sweep through the galaxy.
And the most terrifying sterilizing mechanism is the gamma-ray burst, or GRB.
These are the most powerful phenomena in the known universe. A single GRB can pour out more energy in a few seconds than the sun will generate in its entire 10 billion year lifespan.
If a GRB occurred within a few thousand light years of us, it would strip away the Earth's ozone layer, exposing the surface to sterilizing levels of ultraviolet radiation for thousands of years.
It would cause widespread devastation and mass extinction. Over billions of years, mass extinctions due to these astronomical hazards are just inevitable across the galaxy, which suggests planetary systems are very precarious places.
Okay, so assuming a planet somehow manages to get a perfect stabilizer like the moon, and a thermostat like plate tectonics, why are the evolutionary steps themselves so rare?
The biggest initial hurdle is that abiogenesis is rare. Solution 65. The fundamental process of life arising from non-living matter.
The famous quote from biologist Lynn Margulis is perfect here. The gap between non-life and a bacterium is much greater than the gap between a bacterium and man.
And what's fascinating is that on Earth, life arose astonishingly quickly, within a few 100 million years of the crust cooling enough to support liquid water.
Which might seem to suggest that abiogenesis is easy.
But Bayesian analysis suggests the opposite. The fact that life arose early here does not imply abiogenesis is common elsewhere. Our very existence is consistent with the probability of life arising spontaneously being exceptionally rare.
Maybe a 1 in a trillion event across the whole universe. We know it happened once, but that tells us nothing about how frequently it happens everywhere else.
And if that hurdle is cleared, we hit the second major bottleneck. The prokaryote-eukaryote transition is rare. Solution 67.
For the first billion years or more of Earth's history, the only life was simple, single-celled prokaryotes, like bacteria.
Prokaryotes are small, about 1 micrometer across. They lack a nucleus, and they're energy efficient, but really limited in complexity. Eukaryotic cells, which make up all animals, plants, and fungi, are immensely more complex and large, often 10 to 100 micrometers. They have a nucleus and specialized organelles, like mitochondria.
And the emergence of that sophisticated eukaryotic cell, which is required for multicellular life, took 1 billion years on Earth.
1 billion years. It's believed to have arisen from endosymbiosis, where one prokaryote engulfed another, leading to a massive leap in size and complexity. The mitochondrion, in particular, solved a huge energetic hurdle that prokaryotes couldn't clear, allowing for that leap.
And this transition, occurring only once in 4 billion years, might be the true great filter.
The galaxy could be filled with planets just teeming with hardy but simple microbial life that never achieved the complexity required to develop into animals.
And finally, even if complex animal life does arise, there's no guarantee it will lead to communicating ETCs if it lacks the capacity for the most powerful tool we have. Language is unique. Solution 71.
And we're not talking about basic animal calls or simple alarm signals. Human language is an infinite system. We can construct an infinite number of sentences and abstract ideas from a finite number of words, because our language is rule-based. It has grammar. It's not just a list of stored responses.
This complex rule-based communication is critical because without it, ETCs, no matter how clever they are unlikely to achieve the abstract, cumulative knowledge required to develop high technology.
Like building radio telescopes or launching probes. We have a perfect terrestrial example of this intellectual stagnation. Think about Neanderthals and Denisovans.
They were highly intelligent hominid species who were around for over 100,000 years. They were tool makers, capable of crafting sophisticated stone tools.
But their technology just stagnated. They showed very little significant innovation over millennia. They eventually went extinct without ever inventing something as simple as a wheel, much less advanced technology.
Their intelligence was enough for survival, but maybe not enough to achieve the cognitive leap required for high technology or abstract rule-based communication.
Which suggests that even achieving intelligence at the human level is not automatically a guarantee of achieving a technological civilization. The gap between abstract thought and the ability to codify and share complex scientific knowledge across generations might be the final filter.
So we've gone down 74 different paths to try and understand the Great Silence. We've looked at the whimsical and conspiratorial ideas that they are here. We've explored the technical limits, the tyranny of speed, the light cage limit, and the idea of transcendent post-biological entities who are just too cold and efficient to talk to us.
And we've looked inward, contemplating the terrifying possibility that the great filter lies behind us, making our existence an impossible fluke.
The sheer volume of serious, detailed, but completely mutually exclusive solutions is the true measure of the paradox's power.
It forces a fundamental, sharp humbling upon us.
It reminds us that our species' most renowned scientists, from physicists arguing for rapid galactic colonization to biologists arguing for extreme planetary rarity, they wildly contradict each other. Future generations will look back at us, puzzling over this question, and they'll inevitably think, wow, they really had no idea what was going on.
We are, at best, operating with a tiny, incomplete set of information about the universe's ultimate structure. And this leads to a powerful choice. The paradox demands we reconcile two opposing philosophical ideas about our place in the cosmos.
The French biologist Jacques Monod wrote that man at last knows he is alone in the unfeeling immensity of the universe, out of which he has emerged only by chance.
That's a melancholy thought, but maybe not the saddest outcome. The source material challenges us with an even more profound dichotomy. The true tragedy is not if we are alone, but if the only species possessing consciousness.
The only species that can light up the universe with acts of love and humor and compassion and scientific inquiry.
Extinguishes itself through acts of stupidity or ignorance before fulfilling its potential.
If we survive the existential risks we face now, the potential for self-destruction through runaway climate, uncontrolled AI, global conflict, we inherit a vast, silent galaxy to explore and make our own. The Great Filter is either behind us or it's ahead of us.
That's the challenge Fermi left us with. If there is no one else out there to break the silence, the responsibility for consciousness and for the future of the cosmos rests squarely and solely on our shoulders.
It's a concept worth carrying into your own future exploration of this deep, deep dive.